Good evening, ladies and gentlemen. Welcome to Reference Point. I'm your host, Dave Coker-Hook, and this evening is going to be a little bit different from some things on our usual show because I'm going to take you and ideally myself into a deeper understanding of this thing we call the physical universe, because I have with me today Larry Silverberg, who's a professor at North Carolina State University in Raleigh, North Carolina, and he's going to talk to us about this thing and what it is that really makes up whatever we see around here and the experiences we have. So here he is, Larry. Larry, welcome to Reference Point. Appreciate you being here.
Well, thanks for having me, Dave. This will be great.
I think it's going to be real interesting and a lot of fun. Now, I was looking at some of the information that you had shared with me, and I understand that you are at the Department of Mechanical and Aerospace Engineering there at North Carolina State. And yet we're going to be talking a lot about things that are kind of related to physics and astrophysics and blah, blah, that sort of thing. So how do those two things relate? How did you get from mechanical and aerospace engineering into taking a look at physics-like things?
Well, basically, I'm what's called a dynamicist. Okay, so I study motion, and that includes things that are very basic, the very basic aspects of motion, why things move, all the way to how things move. So in engineering, we have a lot of applied focus on how things move, but also just why things move at a very, very fundamental level. And my specialty is something called four-dimensional geometry and four-dimensional vector fields. And that's you could say the mathematical foundation that gives you, or that enables you to describe basic physical processes, at the most basic level. So that's, in a nutshell, why and how things move.
Okay. And why and how things move, I think, is an interesting way of putting it, and I can see why understanding why and how things move actually makes sense and has impact on me as a guy who goes to work, jumps in a car and drives down the street, or somebody that's studying how to send a rocket from here to Mars, or how to help your grandson or nephew or whatever build a Lego. The Lego thing, because it's interrelated, isn't it?
It is, and I guess a good tangible way to put it is, students when they're young, they get into college and they take these basic classes. Whether they're in physics or in engineering, they take classes called statics or they take classes called dynamics. Mm-hmm. Okay? And these are the building blocks. And after that, they use those building blocks to kind of build models and to figure out how things work and to make new things that work in new ways.
Okay, great. Well, we're going to talk today about a new way of looking at things that you have been involved in researching, I guess is the right way to term that. And I came across you actually by virtue of an article that I saw online that was in a publication called The Conservation, called Fragments of Energy, Not Waves or Particles, Maybe the Fundamental Building Blocks of the Universe. And in the fourth sentence at the beginning of this, it says, we propose that matter is not made of particles or waves, but more fundamentally that matter is made of fragments of energy. I want to dive into that, but I'm hoping that we can start by having you kind of explain in layman's language what really is a particle and what really is a wave. I kind of have a fundamental understanding. People think of a particle as this thing that you can see, feel, taste, touch, measure, whatever, and a wave as something that, like you sit there at the ocean and you watch it go up and down. So there's a wave, but I don't know that we all fully understand what really they are and what the difference is.
Okay, so a lot of it has to do with our perception of what substance is, okay? What things are, and we actually use two words to describe substance in everyday language. We use the word matter and we use the word energy. When you think of the word matter, you think of something very tangible, something that you can touch, that you can grab. When you think of the word energy, you think of the energy around us, something more distributed, kind of like the electromagnetic waves that make wireless communications. You know?
Right, right.
So we actually have these two ideas of substance, and in engineering, in the technical world, we actually have a way to model mathematically what we mean by a particle, something that you can grab. Mm-hmm. And it's a very different way, different kind of math that we would use for electromagnetic waves. Okay. And so historically also, if you look at physics historically, Sir Isaac Newton in 1687 published Principia, and that was the beginning in science of the concept of a particle and the mathematics of it. And then about 150 years later, we brought in science, we brought optics and electricity and magnetism together to create something called electromagnetism or electromagnetic waves. Okay. And then we had this idea that things are made of waves. So what happened was in science.
Wait a minute, that things are made of waves?
Well, that substance is like a wave, you know, energy. The idea of energy comes in, of energy being distributed, and for the most part, you can't see it. Maybe sometimes you can see it, but this idea of waves was one idea of substance. Before that, Newton had the idea of particles.
Okay.
And that was the first time we actually could kind of describe it mathematically and actually start to use it and make things out of it scientifically. So you really kind of have in the history of science, if we look at it kind of in science and the history of science, we have particles are things that you can touch and grab, and that comes from Newtonian mechanics. And then we have kind of electromagnetism or wave mechanics, which comes 150 years later. And each of those gives us two different ideas of substance. The first one gives us the idea of things that you can touch, and the second gives you the idea of these kind of waves radiating through space.
Okay.
So go ahead.
Two very different perspectives, and how do they come together?
So it's kind of interesting, kind of how history works its magic, I guess. The particle idea, after it came out, historically, everybody said everything must be particles, even light must be particles.
Oh, yeah, right.
And they had these different theories on it. Well, then the pendulum swung. After electromagnetism came out more recently, people said, well, everything is a field, is a distributed thing, and that's everything. So the pendulum had swung the other way. The problem was that the concept of the particle is missing something, and the concept of the wave is missing something. So let me try to, I want to try to describe this kind of instinctively, okay? So the idea of the particle, you look at something, you see this object, and you say, okay, it exists at this location, but
yeah, my glasses, for instance.
Yeah, but it doesn't exist anywhere else, okay? Right. And it's a very practical way to look at things, but it isn't really fundamental, because even that idea is missing something. It's kind of like a particle is like a castle surrounded by a moat, and the moat prevents anything from influencing it. Nothing can get in and nothing can get out. But the fact is, these particles, we know they influence each other, okay? Okay, yeah. And so the idea of the particle, of this object that exists in isolation, isn't exactly right, because we know that they're exerting forces on each other and influencing each other. So the particle concept in itself is lacking something, okay? Now the wave concept, this idea of waves permeating through space, is a fine idea, but what created those waves? Where did those waves come from? So that
question that I had, was as you were talking about that came to mind to me. Where do they come from?
Exactly. So what happened was, in our minds, we created these two ideas, and historically we tried, after Newtonian mechanics, to make everything a particle, but it didn't work because it was missing something. And then electromagnetism, we tried to make that everything, the field concept, but that didn't really work because it was missing something.
Right.
So there really is something conceptually that's much more fundamental, a more fundamental building block, if you will, to describe things. Okay. And that's what, and by the way, what I'm describing in the journal article, me and Dr. Eischen describe in the journal article, in some ways it's new, and in other ways it's not new at all.
Right.
It's new in the sense that, and this is in the weeds, it's new in the sense that we formulated the mathematics to show why it's new, with the proper mathematics.
Right.
What's not new is that lots of people have always thought that things are made up of energy, and that you can think of everything around you as energy, and that the building blocks are little kind of pieces of energy. The idea itself is actually very intuitive.
Right. But
Go
I
ahead.
think that we're not, as we go through school. I mean, when I was in high school and college, and I took my classes in science and chemistry and physics and biology and various math classes all the way up through calculus and stuff like that, or to calculus. And that was the one that really threw me. It just what you've described as these two concepts, each of which, when you look at them deeply, are missing something. There's just like something that doesn't quite add up, and so therefore we have to look at a more fundamental thing. It's what's that idea? That's the simplest truth is real. The simplest item is usually the right one, is the truth. And so what led you to go in this direction? What prompted you and your colleague to say, we got to take a closer look at this, because I think there's something really there?
Well, a part of it, that's a really good question. What drives a person to do this? When you look at electromagnetic phenomena, or you look at particle phenomena, they have so much in common. You can't help but think that there's some connection between them. So being a fellow who basically has worked in these areas and seeing those connections probably motivates me more than anything else. And then also the fact that it's kind of philosophically or logically flawed. The idea that everything should be starting from one or the other is kind of logically flawed. It's actually a puzzle. I would say that if you asked me what motivated me to work on this, number one, I love puzzles. And number two, I happen to be a dynamicist. This is coincidental. I happen to be a dynamicist that works in this area of four-dimensional vector fields and four-dimensional math. And that is the foundation, the mathematical foundation that you need to do this kind of stuff. So I happen to be in the right field. I also love a really good puzzle. So it was a combination of a number of those things in my background that about 15, 20 years ago, I started seriously looking at this.
Got it. Well, very cool. Well, we appreciate that. This nice confluence of interest and background. That's a very cool thing. So, can you, in layman's terms, explain what this fragments of energy concept actually is, and then we can go into how
Sure.
it might be
applicable
to the real world?
Sure. So when we talk about building blocks of things, what comes to mind to most people might think, oh, look at the atoms. They're made up of electrons and protons and neutrons, and
Right.
even the neutrons themselves are made up of subparticles and so on. Or you might say, well, we could look at the Earth and we could think of it as a particle when we model things. So when we think about building blocks, the fragment of energy is just a concentration of energy, and it's probably closest to the idea of the particle, because a particle can be a tiny particle. It can be, it's called at the atomic scale. Okay, you can call something a particle, or you could call the Earth a particle. And if you want to try to model how the Earth and the Sun, how the Earth's orbiting around the Sun, the Earth could be a particle. So the word particle applies at all different kinds of scales. Electrons, the elements, don't. And an electron is specifically at a particular scale. You see an electron or you see a proton. Okay, so some elements are kind of less versatile than others.
Okay.
The particle is very versatile. The fragment of energy is like the particle. It's just a concentration of energy. Just like a particle, it can be applied at different scales. So can the fragment.
Can it be measured?
Yeah, it's a distribution of energy. You actually see fragments at all different levels. When you see the energy radiating from an electron, that can be like a fragment. When you see the energy coming off of the sun, if you go outside at night and you look at the beautiful stars in the sky, when you are looking at those stars, they're very far away. They look like points of light. Those are fragments of energy. However, imagine you were in a spaceship and you started traveling close to the star. When you get close to the star, the complexity of the star comes into view. You wouldn't model it at that point as a single fragment. At that point, it would be a bundle of hundreds and thousands and millions of fragments.
Right.
So you have to remember that what we do in science is we model reality. And when you model reality, it's not the same thing as reality. Because when you model reality, it's at a perspective,
Right. Oh yeah. Right. Okay. I get that. It's from wherever you happen to be, the way you see things from this level of distance, shall we say, is not necessarily the same as when you get close to it. I mean, I've seen this.
It's fascinating.
This is maybe an example. Maybe an example of what I mean by that is my family and I would make these jigsaw puzzles, right? And beautiful jigsaw puzzle. You make up the jigsaw puzzle, and it's a picture of something like one was a picture of Abraham Lincoln, but each one of those puzzle pieces had on it small little photographs that came from the time of Abraham Lincoln. All right, and this is an actual puzzle. And so when you get real close to it, it's like, holy mackerel, it's not just this picture of Abe. It's like all these other things. Exactly.
Yeah. Look what happens when you get in a plane and, from a distance, you see the clouds. Then you go through the clouds and now everything looks completely different.
Right.
So you could say that in engineering and in biological sciences and all the sciences, it's a perspective. We have a certain perspective from a distance, and the images and the relationships are all at that scale. So what we say is that that models of reality are at a certain scale of view, a scale or perspective, but yet reality itself doesn't have that scale. Now, some people might think that's a disadvantage. Somebody might say, oh, that's terrible. Science is only at a particular scale. But actually, all thinking is at a scale. We always are thinking at it. And if we didn't have an ability in our thinking to focus on a particular scale, well, we would lose focus. We'd get bogged down, and we'd say, no, come on, you're in the weeds here. Let's get out of the weeds. Let's kind of look at this on a little broader, or let's now focus in a little bit more. But even our models of reality and the way reflect the way we think. We think and we model our reality at a particular scale, and it's a very basic thing.
Okay. We have, by the way, approximately 10 minutes left in our segment of the show here. So I'm going to ask you now if you might be willing to sit with me through another part of this conversation, because I have a feeling we're not necessarily going to get to the end point that we were hoping to get to. We've been laying some foundational information, and I think this is important from the standpoint of understanding like you said, a perspective of what it is that we're talking about and how this concept of fragments of energy actually have relevance. I'm excited about taking this conversation to the point of not just the theoretical and esoteric side of it, but let's get down to what it really means from practical possibilities. And I recognize there's more research that has to be done. There's more understanding of the environment. There's probably mathematical things that have to be tweaked a little bit so that you can really do it. But if what we're talking about is the way that the universe is actually made up, then these fragments of energy seem to me to be if you can understand it, you can access it, and you can control the way it flows, then you are in a position to have a significant impact on what we do, how we do it, when we do it, where we do it, and the, the whole different kinds of physical challenges that we experience in our world today. So
Well,
I want to get there.
yeah,
But I don't know.
I'd love to come back. I would enjoy that.
Okay, cool. So we'll get to that probably in the next segment. We got a little bit more time left here. So, okay. So is there anything that we've talked a lot about this, and you sent me some graphics and stuff like that. Is there anything within the graphics that would help? Because some people learn better from things that they see, and others from things that they hear. Is there anything that you sent?
Yeah, I think that PowerPoint is actually pretty good because when what I'm really are saying is that the fragment of energy is, you should start with a fragment of energy, right? And then you go from there. And really what myself and my co-author, Dr. Eischen, that's right. So what I'm going to do is I'm going to describe to you how we actually start the argument, how we start the discussion of kind of what things are. Okay.
All right.
And it's kind of a mathematical argument, but you don't need any math because I want you to appeal to your own intuition a little bit. So I drew a line on a sheet of paper there, and you see that little line.
Yep.
And when I drew that line, I didn't pick my pen off the sheet of paper. I kept my pen on the sheet of paper. There's no gaps on the line. Right. Now in mathematics, we say that line is continuous, and so continuity really is kind of the same thing as just drawing a line, and they call that today just continuity or ordinary continuity. Now I'm going to call it ordinary continuity because there's more to the story than just ordinary continuity. So if you can hit the button there once, and now what I'm imagining doing is I'm filling the entire sheet of paper with lines. Okay. And if those lines never cross each other, they don't begin or end on the sheet of paper. They just kind of flow through the sheet of paper. The lines never cross. They don't begin or end or cross. Then we say that all of those lines satisfy something called vector continuity. So there's scalar continuity and there's vector continuity. In school today, the young kids, they learn about scalar continuity, the ordinary continuity, but they don't learn that much about vector continuity. If you can hit the button again. Okay. So what I'm going to do is I'm just going to tell you what vector continuity is.
Oh, good.
So when I say that a bunch of lines never cross and they flow, by the way, flow is kind of the everyday word for vector continuity. So when I say you fill up a bunch of lines and they're flowing in space and time, then what that means is none of the lines are crossing, and that's called but there's an equation for this. And I guess the way a mathematician might say it is an equation that says that all these lines satisfy vector continuity. That would be a fancy way of saying it. They're flowing. Okay. So with the first thing I'm doing, I drew a circle, and that's going to be a region. Okay. Now if you can click again, and I'm just going to focus in on one bit of that region, one segment of that region. Some of those lines are flowing out of that region, right? In that little area. If you can hit the button again, okay? And actually, if you count the number of lines that are leaving that region, that's an equation right there in front of you for the number of lines that leave that little region. Okay. Now, a line going out of the region is positive. Lines going into the region are negative. Okay. So what we're going to do is we're going to add up we're going to count the number of lines leaving that little region, but we're going to count it all around that red region. Okay. Now, if you hit the cursor again, now what we have is an integral sign. That just means with a little circle in it. That just means add up all of the different numbers leaving the region all the way around it, and that has to equal to 0. The sum of all of that has to equal to 0. A mathematician.
Okay, because the positive and the negative are going to cancel each other out.
Yeah, I mean, if you just kind of look at this, if you just look at this picture and you imagine counting the number coming in, the coming out, you can see that every line coming in eventually leaves.
Got it. Okay.
Okay, yeah. So that is an equation. It's called the integral form of vector continuity. Big words, but it really just means that the energy is flowing. Now that line is a line of energy, and in fact, in modern physics, the energy has a value, but also the line itself has a direction. So in vectors, you have magnitude and direction for a vector. And so what you do is you create this whole bunch of lines of vectors. It's called a vector field. It's a four-dimensional vector field of energy that's flowing. And this is actually how we start, okay? This is actually the beginning of the theory. It's the novel way the theory begins of flow. And the reason it's fundamental is because from the idea of flow of energy, you then can get things like energy conservation. You can get the form of the fragment of energy. You can get wave behavior, what's called Maxwell's equations. So flow turns out to be this little picture, and the idea of flow turns out to be the starting point, which gives you a lot of the other, actually gives you all of these equations in physics that drive and tell you what's going on with particles and what's going on with waves.
That's pretty interesting. And actually, the way you explained that was clear enough and simple enough that I was able to pretty much understand it. So I thank you for that, and I assume that's going to be the case, hopefully, for my our viewers as well. You did say one thing that I had to do with how these waves flow, the lines that you were talking about, and they never cross, etc. I suppose you're talking about once it goes in a particular direction, that it doesn't, the direction doesn't alter such that it comes across another flow line, another wave.
Well, first of all, what we're saying is that nothing ever crosses if you're in your picture, you're looking at all of the dimensions of space and time. So if I'm focused on something, like if I don't see time, I'll tell you a funny story about how intuitive this all is, and about crossing and stuff, and fooling people, you know. So if you think about it, through the ages, there are these magic tricks. People have been doing magic tricks now for hundreds and hundreds and thousands of years. And what does the magician do? The magician says that I have something over here, and I'm going to make it disappear, and then it's going to reappear somewhere else. Okay? Right. If you think about it, that's called the violation of continuity. Okay? That means that somehow it got there, not continuously, but it got there somehow, and it disappeared and reappeared. Okay? Right. The way you do these tricks is by basically saying, don't look over here, you know, look over here. Right. And what you're doing is you're saying you're not looking at all of the dimensions of either space or time. Okay? And so what's happening is, instinctively, the idea that everything is flowing and everything is continuous, in fact, is so instinctive, it may not have been understood mathematically, but it's so instinctive that people have been doing magic tricks based on this now for 1,000 years.
For thousands and thousands of years. Oh, okay. That is a very interesting place for us to end off this first segment of our conversation, because I've got to wrap this up, and then if you don't mind hanging out for a few minutes while we get everything reset here, we'll start another part of the conversation and take it to the deeper level. So does that sound okay to you?
That sounds great.
Great. Well, ladies and gentlemen, I want to thank you for joining us here at Reference Point for this segment on fragments of energy, and hang tight, because we're going to come up with another one in just a few minutes. So thanks for being there, and we'll see you next time on Reference Point.